Okay, it's Brian, and we're taking a look at the review and practice problems from day 6, and this spans the whole textbook. It spans everything we've talked about in physics, and the idea is each one of the scenarios that you have is going to bring up some facts about the world, a physical situation, and then we're going to use physics to explain and explore it. That's basically the idea. So you're going to go ahead and take a look at the scenario, look at the questions, look at the problems, and the questions and the problems are just giving you a chance to show you using what you've learned. Okay, so let's take a look. First part is you don't say, the first scenario. So our ears are remarkably sensitive, and we've seen that if you're talking at a reasonable level. The intensity is very small at a reasonable distance. Suppose someone is speaking at a steady pitch of 250 hertz at this level. What is the approximate wavelength of the sound? Well, we know that we have this basic relationship for sound and other traveling waves, that the velocity is equal to the frequency times the wavelength. We're given the frequency, and we also know the speed, and the speed of sound in air. We said we could just use 340 meters per second as a good average value for that. With those two numbers in hand, we come up with a wavelength of about 140 centimeters, about 1.4 meters. Next up, it's asking about the physics of your vocal tract. So if you open your vocal tract so it looks like an open-closed tube from your vocal cords to your open lips, the first formant is about 250 hertz. What approximate length does that imply for your vocal tract? Well, remember, we said we have an open-closed tube. I'm going to have standing wave modes, and the open end of the tube acts like a node, and the closed end works like an antinode. And the frequencies of the different modes looked like this. The frequency of the mth mode was m times v over 4l. Oh, and the first formant, that is for m is equal to 1, and so I put m is equal to 1 here. I know the speed of sound in air is about 340 meters per second. I know the frequency of the first formant is 250 hertz. The only thing I don't know in this expression is L, and I can calculate the value for L. If I do that, I get 35 centimeters, which is a bit over a foot. And given how my body is put together, that seems like a reasonable number. Now for the problem, we're going to do some calculations with intensities and powers and all that kind of stuff. So first question, how much acoustic power is the person emitting? And we expect that to be a small number. I mean, that's part of the problem statement. Talking a normal conversational level requires very little energy input. So when you speak, the sound that you emit travels out like a wave. Travels out like a wave from a point source. And as we've seen, the intensity from a point source of sound looks like this. The intensity is the power of the source divided by 4 pi r squared. Rearranging that, I get the power of a source is equal to the intensity times 4 pi r squared. Well, you know the intensity. We're told what that was. We're given a value for it. And you know r is just the distance from the source. That's just 1 meter. So with both of those numbers in hand, I can calculate a power of the source, and I get 1.3 times 10 to the minus 5th watts, which is a small number, as we expected. And to show you how small this number is, the question says this: suppose you were to take the sound of your voice and take all the energy from it and use it to heat a cup of water. How long would it take you to change the water temperature by 1 degree Celsius? And since it's a tiny power, I expect a lot. Now let's think about this. If you are emitting power at a rate p, okay, and you do that for a time delta t, you have put out a certain amount of energy. Now, if all that energy goes into heating water, so we'll take all that energy and it goes into heat, which is put into water, and it changes the temperature by delta t, the heat required to change the temperature of a mass of water by a temperature delta T is given by m times c times delta T. So P times delta T, the power you emit times the time for which you emit it, is equal to m times c times delta T. M is the mass of the water, and it's 0.35 liters of water. But for water, 1 liter is equal to 1 kilogram. Okay, that's given the density of water, so we have 0.35 kilograms. The specific heat of water is 4,190 joules per kilogram. per degree Kelvin, and the change in temperature we're looking for is 1 degree Celsius or 1 Kelvin. So I can calculate how much heat is necessary, and that is provided by my acoustic power for a time delta t. With all those numbers in hand, I can calculate what delta t is, and if I do that, I get 1.2 times 10 to the 8th seconds, which is a bit more than 4 years. So this is really not a practical strategy for heating water. And the whole point of this problem was not that this is a practical strategy, but that this is an interesting way to dramatize how little acoustic power you put out when you speak. Next scenario. And this one has to do with leaping kangaroo rats. Okay, and so this was from a research paper, and the people took kangaroo rats and they put them in some sort of a container like this. Okay, so they have the kangaroo rats, and the kangaroo rats are in there, and they forced them basically to jump straight up. So they had to jump straight up. And that is not their natural way of jumping, but even when that's not the natural way of jumping, they were capable of doing quite a remarkable vertical leap. And you saw in the data, a 0.12 kilogram rat forced to make a vertical leap was able to exert a 5 Newton force on the ground, and it could do that for a time of about 0.1 seconds, and that was an approximately constant force. Let's take a look at the questions first, and then we'll come back to the problem. First piece, what was the approximate net force on the kangaroo rat for this jump? Well, if a kangaroo rat is pushing off on the ground is pushing off on the kangaroo rat. And if the kangaroo rat is pushing down with a force of 5.0 newtons, the ground is pushing upward with a force of 5.0 newtons. But then, too, there's a weight force. And the weight force on the kangaroo rat, that's just m times g. And if I work out what that is approximately, that's about 1.2 newtons. And so the net force is going to be equal to the force in the direction of the acceleration minus the force opposite it, n minus w. That comes out to be about 3.8 newtons. And so when we're rounding, we get approximately 4 newtons is the right answer to choose here. Now, here's a quick pro tip. Going forward, when I have to use the force in a calculation, I'm going to use this value, not the rounded value. You don't use that one, okay? All right, next piece of the puzzle. At what approximate speed did the kangaroo rat leave the ground? Well, it applied a force. There was a net force on it of 3.8 newtons, and that took place for a time of 1/10 of a second, okay? So we can compute the acceleration this way. The acceleration is just equal to the net force divided by the mass. That's equal to 3.8 newtons divided by a mass of 0.12 kilograms. So I get an acceleration of 31.7 meters per second squared. And then that took place for a time of 1/10 of a second. And I can compute the change in velocity just this way. The change in velocity is just the acceleration times the time interval. Net result is the velocity when the kangaroo left the ground was about 3.17 meters per second. And if we look at the closest value available in the answers, that's 3 meters per second. For the problem, we're asked to talk about the leap. Okay, how high did the kangaroo rat go? And how long was it in the air? Okay, so first off, let's take a look at the how high did it go. Now the kangaroo rat left the ground at a speed of 3.17 meters per second. And it made it to a height I'm just going to call delta y. Okay, made it to a height delta y. When it got to its highest point, its final speed was just 0 meters per second. We know that that's true. So my initial speed is 3.17 meters per second. My final speed is 0. And the question is, what is delta y? Well, for this part of the problem, let's not worry about the time. And if we don't worry about the time, my basic relationship for motion with constant acceleration, which this is, okay, that doesn't use time, looks like this. Vf squared equals vi squared plus 2 times a times delta y. And we know the acceleration. This is just free fall. So the acceleration is equal to negative 9.8 meters per second squared. I know the initial velocity. I know the final velocity. I know the acceleration. The only thing I don't know is delta y. And if we compute delta y from this equation, we get that it's 0.51 meters or 51 centimeters, which is impressive for this little creature, and also comparable to other values that we've seen. We've seen other creatures which were leaving the ground at about that speed, and that's about how high they got. Next question, how long was it in the air? Let's then do the whole trajectory. The kangaroo rat leaves the ground at 3.17 meters per second, and let's make that positive. When it returns to Earth, it's moving downward at the same speed that it left the ground at. So it touches down at negative 3.17 meters per second. So therefore, the total change in velocity during its flight is negative 6.34 meters per second. That was its change in velocity. And I can compute a time interval by just saying the change in velocity is equal to the acceleration times the time interval. Well, I know the acceleration, it's free fall, so it's negative 9.8 meters per second squared. I know the change in velocity, and so I can compute the time interval. And if I do that, I get a time interval of 0.65 seconds. And again, that is comparable to values that we've seen in other situations for leaping creatures. On to the next scenario. And the next one has to do with heat in a couple of different ways. First off, we imagine using a laser to heat a spot on a tumor. And the question asks this, the first question asks this, what is the approximate frequency of the laser? Well, for any traveling wave, the frequency is equal to the velocity times the wavelength. And for a laser, it's visible light, the speed is 3.0 times 10 to the 8th meters per second. And we know what the wavelength is. Okay, you're told that the wavelength is 800 nanometers, or 800 times 10 to the minus 9th meters. With that information in hand, I can calculate the frequency. And if I do that, I get a frequency of 4 times 10 to the 14th hertz. Next question, approximately how much energy is delivered to the tumor in 1 second? Well, the power delivered is equal to the intensity times the area. And remember, that was our basic definition of intensity. What is the area? Well, you're using the laser to illuminate a spot of a certain size. Okay, spot has got a certain diameter, 0.5 millimeters. So the area of the spot is just going to be pi r squared. We'll assume it's a circular spot. The radius is 0.0025 meters. With that information in hand, I can calculate the area. The other thing I'm told is the intensity, and that is given in the problem statement. So I get a power of 0.785 watts, which doesn't sound like that much power, but it's delivered to a very, very tiny spot. Okay? How much energy was delivered? Okay? In 1 second, the energy is just equal to the power times the time interval. So if it's 0.785 watts, that's 0.785 joules per second for 1 second is an energy of 0.75 joules, or approximately 0.8 joules. Next piece, we're looking at the energetics of exercise. So we suppose a person is running up a series of stairs. And let's think about what happens as the person does this, okay? What is happening as the person does this? The person is changing potential energy. So they go from the bottom to the top. They have gone up by a height, h. They have changed their potential energy by an amount, m times g times h. Okay, so they've changed their potential energy. And in efficiency terms, we can say this is what they get. So let's look at how much the person had to, actually we can calculate that. Let's go ahead and do that. So the amount of change of potential energy of the person when they go to the top is 188,000 joules. But then we can use our efficiency to calculate the chemical energy used, the metabolic energy used. Because efficiency is what you get divided by what you have to pay. And what you get is potential energy. What you pay is the chemical energy, the metabolic energy that your body uses, okay? And so if I do that, I calculate the metabolic energy. It's 4 times this change in potential energy because we assume that the efficiency is 0.25. We said that people are about 25% efficient. The metabolic energy the person uses is 752. That wasn't a very good two. 752,000 joules. So the change in thermal energy is just going to be equal to the metabolic energy minus the change in potential energy, because her body uses a certain amount of energy. Some of it goes to changing potential energy. What's left over turns into thermal energy, and the thermal energy that we get is equal to 564,000 joules. I'll mention too, this relates to our basic energy equation like this. We said if you have chemical energy as part of the picture, chemical energy plus initial potential plus the kinetic plus the work is equal to the final kinetic plus the final potential plus the change in thermal. And looking at this, there's no initial kinetic energy. She's not moving at the start. She's not moving at the finish. There's no initial potential energy. No one's doing any work. She's not jumping on the elevator. The initial chemical energy that's stored in her body turns into final potential energy plus the change in thermal energy. And we can use the efficiency to relate those different quantities, and we find that she gets this much extra thermal energy at the top. And if she doesn't want to warm up, she's got to exhaust that into the environment. So all of that energy is deposited as heat into the environment, and it's doing that by evaporating water from her skin. Now the energy for evaporating water is just m times LV. LV is the heat of vaporization, and its skin temperature, we were told that was 24 times 10 to the 5th joules per kilogram. Don't use the 22.6 value from the table. That's boiling, but we're not boiling, we're just evaporating. And we know the change in thermal energy, that's 564,000 joules. So we can calculate how much water has to evaporate from her skin. And if we do that, we get a value for the mass of 0.24 kilograms. And that's about 1/4 of a liter, so it's not very much, as it turns out. And that is consistent with other numbers that we've seen. Let's take a look at our last scenario. And our last scenario has to do with trout. And trout are capable of intense bursts of acceleration. Okay, and I looked at this in a paper. And what the people were doing is they're basically looking at how temperature affected trout. But there was really good data on trout's accelerating abilities. A 14-centimeter trout with a mass of 27 grams could accelerate from rest for a time of 0.078 seconds that would allow them to traverse this much distance. So basically what they did is that they made the trout go a certain distance, and they did it at essentially constant acceleration. They went this far over this time. And that is a tiny amount of time. That is less than the time that it takes you to a blink, which is about 0.1 seconds. So in 0.1 seconds, the trout moved several inches starting from rest, which is kind of impressive. First piece of the puzzle, what is the trout's approximate acceleration during the burst? Okay, well, acceleration, the way we can calculate that is we'll just use one of our basic equations for motion with constant acceleration. And we'll use this one, xf is equal to xi plus vi times delta t plus 1/2 times the acceleration times delta t squared. Now the initial speed is 0. The trout starts at rest. Let's take the initial position as 0. The final position will take us 5.4 centimeters or 0.054 meters. And another time interval, that's 0.078 seconds. With all that information in hand, I can calculate the acceleration. And if I do that, I get a value for the acceleration of 17.8 meters per second squared, which is approximately equal to 18 meters per second squared. Question 2, what was the trout's approximate final speed at the end of the burst? Well, that's fairly straightforward to calculate because we know the final speed is just equal to the acceleration times the time interval, because the initial speed was 0. The acceleration is 17.8 meters per second squared. The time interval is 0.078 seconds. And so I end up with the final speed of 1.38 meters per second, or looking at the closest value in the table, 1.4 meters per second. Next question, what was the trout's specific power during this burst? Okay. Well, power generally is equal to the change in energy divided by time. I don't want you to use power as equal to force times velocity. That doesn't really work here, because that is really for like doing work. That is really for doing work. So I've seen people try to use this as like force times velocity delta x over delta t. That doesn't really work because, one, the velocity is not constant, the power is not constant, so that's not working for you. But also, two, that is a version of the power relationships that is about doing work, and this isn't doing work. It's an internal conversion. The trout takes chemical energy in its body and it converts it to kinetic energy because the trout is getting up to speed. So a better way to calculate is to say that the power, and this is going to be an average power because it will vary, is going to be equal to its change in kinetic energy divided by the time interval for that change. Well, the trout's initial kinetic energy is 0. So the change in kinetic energy is just going to be equal to the final kinetic energy. So the power is just equal to the trout's final kinetic energy divided by the time interval for the acceleration. And the kinetic energy is 1/2 m times v/f squared. And we calculated the final velocity up here. And we know the time interval. That's 0.078 seconds. And so if I do that calculation, I come up with a power of 0.33 watts. But the problem didn't ask for the power, it asked for the specific power, the watts per kilogram. So I take that 0.33 watts and I divide it by the mass of the trout, which is 0.33 watts, divided by the time interval, which is 0.078 seconds, and I come up with a specific power of 12 watts per kilogram. And that is more than people in your class were capable of, less than some of the things that we've seen for mammals. But for a fish, that's pretty impressive and kind of like comparable to other numbers which we have seen. There we go. And that is the end of our fourth scenario. This is exactly the type of thing you're going to be doing on the exam. So I hope that this practice has helped you, and I'm wishing you the best for the final exam on Wednesday.